Good morning, everyone. So in the last class, we started our discussion on source coding or data compression, and we were basically looking at a model for the data compression problem. So our model for the goal is to, of course, compress a raw file or a source sequence, x1 through xn. We assume that each xi comes from some source alphabet script x, and our fundamental assumption is that the source is random. So we assume that xn is a random sequence and has some distribution pxn. And one another assumption that we will make is that both the encoder or the compressor and the decoder or the decompressor know this distribution xn. So the source statistics are known both at the encoder and the decoder. And in addition, we'll make this assumption that both the encoder and the decoder know the size of the source sequence, n. Right? So this is always available as side information to both the encoder and the decoder. Now, in practical systems, of course, this is not known exactly, but there are ways to sort of encode this as part of the compressed file itself. So if you look at modern compression algorithms like zip or rar, so some of the information like the source statistics, the size, and other algorithmic parameters are generally stored as a header in the compressed file, and the decompressor first reads the header and then proceeds to decompress the rest of the compressed sequence. All right. So now we'll see. So now that we have suitably defined the compression problem, and we saw that there are different, and one can categorize compression into different classes based on the quality of the decompressed file. You can classify compression algorithms into lossless and lossy compression algorithms, and based on the length of the compressed sequence, one can categorize compression algorithms into fixed length and variable length compression algorithms. Right. So right now we'll start by I'll give one. So we saw a couple of examples of fixed length and variable length lossless compression algorithms. So for lossless compression algorithms, if it's a variable length scheme, then obviously the length changes depending on the source sequence, and we measure the performance of such an algorithm using the expected length. All right. Whereas if we're looking at fixed length compression algorithms, then obviously the length of the compressed sequence remains fixed. But now there is an associated probability of error. So the goal is to design compression algorithms with the smallest rate, which is k over n, such that the probability of error is also correspondingly small. Okay. So any questions? Any questions? Okay, so now let's look at a variable length compression algorithm. Okay, so now the goal is to construct compression algorithms, construct a variable length compression algorithm, for which the average rate RAVG equal to expected length divided by n is as small as possible. Okay, and we're basically interested in the regime where n is very, very large. Okay, so that will be our regime of interest. So we have an extremely large source file, and our goal is to compress it to a sequence as small as possible. And we're looking at variable length compression. So we want to make sure that the decompressed file is exactly equal to the original file. Okay, so obviously the mapping from the source sequences to the compressed sequences, it must be a one-to-one mapping, right? No two source sequences can be mapped to the same compressed sequence, otherwise you will not be able to decompress uniquely. Okay, so so let us try to think about what would be a good compression algorithm. Now let's assume that we don't really care about computational complexity. You have all the computational power in the world, and you you know what the statistics are. So the assumptions are that Pxn is known to both the encoder and the decoder. Okay, so this is available as extra information, and Pxn is known, n is known, and you can use as much computational power as possible. Okay, so we don't care if the algorithm that we design is grows only polynomially in n or even exponentially in n. No problem for now. Okay, because what we want to do is understand what is the best that is possible without any constraints. So we want k of xn to be as, sorry, the expectation of k of xn to be as small as possible. So if you were given these constraints, so these are the requirements, how would you go about designing a compressor? What would you do? Anyone?
Uh, Sir, am I
Yes.
audible?
Yes.
So when we want the expectation of k of x, and that is the length to be small,
Okay.
then we will prefer um, smaller number of bits for a high probable. Uh,
Okay. Very good.
well,
So one thing to keep in mind is that if the probability of observing a particular source sequence is high, then you should assign fewer number of compressed bits to it. So the length, so k of xn should be small if p of xn is large, right? So so for a particular realization xn, if pxn is large, then then if you want the expectation to be small, then k of xn should be small, right? Okay, so now can you convert this to a rule? Can you design an algorithm? So what would you do? What would be the best thing to do? So let us assume that I write down all possible source sequences. So we'll assume that the source sequences, the random source sequence, comes from some alphabet, script X. Uh, so I'll write down all possible sequences. So X1 up to Xn. So maybe if I assume that script X is whatever, 0, 1, 2 up to A, the source alphabet has size A plus 1, then this would be all zeros, 0, 0, 1, and so on, all the way up to A, 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 A. Okay. So there are a plus 1 to the n possible sequences, and each sequence has length this, right? So of course I can write down all the sequences in this particular fashion, but what I want to do is, instead of writing it in this particular manner, instead of just ordering them in a whatever lexicographic fashion, let me instead write this in the order of decreasing probability, right? So let's assume that I have xn of 1, xn of 2, all the way up to xn of uh, a plus 1 to the n, such that the probability of observing xn of 1, this particular sequence, is greater than the probability of observing this sequence, and so on, right? So pxn of xn of 1 is greater than or equal to pxn of xn of 2, and so on. Okay, so xn of 1 is the one which has the highest probability, xn of 2 is the sequence which has the second highest probability, and so on, right? If two sequences have the same probability, then it doesn't matter how you order them, you just fix some particular rule. Okay, so now that we have this, how would you assign uh, compressed sequences to this? So
What's a weighted average, sir? Using this as an weighted average attached to each
correct.
of the
So the
symbols.
expected length, of course, would be a weighted average. But what would you? So for example, you have xn of 1, right? What would you assign to this? What code word would you assign to xn of 1? What code word would you assign to xn of 2, and so on? Let's take maybe a simpler example, right? So let's take a concrete example where you have, let us say, 6 sequences. Say xn of 1, xn of 2, up to xn of 6. Okay, you know that this is the highest, this is the sequence with the highest probability, this is the sequence with the second highest probability, and so on. Right, or let's say, since it's not a power, let's say xn of 4. Okay, just 4 sequences, xn of 3 and xn of 4. Right, so maybe the sequences are 1 0, 0 1, 0 0, and 1 1. Okay, so this sequence has the least probability, this sequence has the highest probability. So, and for these I need to assign code words. How would you do it?
So the probabilities, if we know for each of
Okay,
them,
okay,
then as it is in a descending order of probability, we can try to divide it into two parts, like so such that the first part and the second part probabilities are almost same. Like
okay. But is there something better you can do? My claim is that it doesn't matter what the values of the probabilities are. Even without that, I can give you an optimal scheme which does better than anything else. Remember, there are no other constraints.
maybe we can just start for the highest probable one with one bit.
Okay,
And
so obviously this has to have fewer number. So the code word for this should have fewer number of bits than this, or it cannot be any more than the number of bits for this, and so on, right? So what is the smallest thing you can think of? Let's say bit 0, right? And then for this, what would you assign? Bit 1. Now next, what is left for xn of 3? It has to be 2 bits, right? Because you exhausted all possible 1 bit sequences. So now you assign, let us say, 0 0, and then for this you assign 0 1. Now if there were more sequences, how would you go about? You would obviously, for the first thing you would do is try to exhaust all possible 2 bit sequences, 1 0 and then 1 1. Now for the next sequence, well, you can't assign any 1 bit or 2 2-bit code word, so it has to have 3 bits. So then you can just assign 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on all the way up to 1, 1, 1. Once you've exhausted all possible 3-bit sequences, now you have to assign a 4-bit sequence, and so on. Right? And my claim is this is optimal. You cannot do any better than this. Can you see why? So is the construction clear? For the sequence with the highest probability, I assign bit 0. For the sequence with the second highest probability, I assign bit 1. The third highest, it is 0, 0. Fourth highest, 0, 1, and then so on. So I basically I'm assigning code words in a greedy fashion. So for the highest probability, as I assign the shortest sequence. For the second highest probability, I assign the second shortest sequence, and so on.
Sir, starting from 1 bit, like we are increasing the number of bits in all possible code words we have put. So
Correct.
there can't be anything more than this.
Correct. Right. So it's not really possible to do any better because you the way you have assigned it, you've always ensured that. So if you start from the highest probability to the lowest probability, you can't do any better. You cannot. It is not possible to assign shorter sequences to any of these when you're going from xn of 1 to xn of whatever a plus 1 to the n. Right. So, and since the expected length k of xn is summation over all possible, let us say I equal to 1 to a plus 1 to the n. So this is going to be k of xn of I pxn of xn of I. All right. So as p decreases, k increases. Okay. So this is in some sense optimal. Right. Any questions? Okay, so now I'm going to make a small modification to this assignment. Instead of, so the shortest sequence, of course, we started with a 1-bit sequence. It's a very small modification and does not change things much, but just for convenient representation, I'm not going to start with code word sequences of length 1. I'm going to start with code word sequences of length 0. Okay, so I'll assign no bits. So basically, if at the output I see an empty file, then it means that it is the actual source sequence was xn of 1. Okay, so this is just empty, and then for xn of 2 I'm going to assign 0, for xn of 3 I'm going to assign 1, and then xn of 4 I'm going to assign 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, and so on. Okay, so it's just that one tiny modification that I'm going to make, and we'll see why I'm making this modification. It just makes things a little more convenient to represent. But is this okay? So I start with the empty sequence, so length 0 sequence, and then length 1 sequence, length 2 sequences, and so on, length 3, and so on. Okay, so not much of a change. Okay, So now I have this particular thing. Now the question is, can I compute the expected length, or at least get a bound on the expected length of this particular compression scheme? So note that now a decompression can be done uniquely because all of these sequences are different. The decompressor, upon seeing these sequences, you can exactly identify which source sequence uh, is, uh, is the actual thing. So, and the way to do it is that, so of course, this involves a lot of computation because you have to reconstruct this entire table. You have to order all the sequences in decreasing order of probability, and that has to be done both by the encoder and the decoder, right, in order to obtain this particular table. And that involves a fair bit of computation, and we're discounting that. It's okay if it takes a lot of computation. So this is not an efficient algorithm, but it's still going to be an optimal algorithm. Okay. Okay. So now that we have this, let us see what can we get a bound on the expected length of this particular scheme. Okay. So let us look at xn of I. Right. So what is k of xn of 1? It is 0. K of xn of 2, that is that is for the second largest sequence, it is 1. K of xn of 3, it is 1, and so on, right? So for 4, it is going to be 2. For 5, it is going to be 2. For 6, it is going to be 2. For 7, it is going to be 2. And then for 8, it is going to be 3. And so on. Up to what will it be equal to 3?
16.
15, right? So
Yes,
8
sir.
to 15, it is going to be of length 3, because so 8 to 15, there are 8 possible sequences. And then 6 for 16th sequence, it is going to have length 4. And what is it going to go up to?
31.
31. Okay. So now do you see a pattern? So if I had to, if I wanted a general formula for k of xn of I, for the ith highest probability sequence, what would be the corresponding length according to this?
Two to the power n minus 1.
Sorry, can you repeat?
2 to the power n minus 1.
2 to the power n minus 1, are you sure?
Log of
So it has to be in terms of I, right?
Sir, log of I plus 1.
You're saying log of I plus 1, are you sure? Because here xn of 1 is 0, right? So if you put I equal to 1, you should get 0. If you put I equal to 2, you should get I equal to 2 or 3, you should get 1. I equal to 4 to 8, you should get 3, and so on. So you're close, it's log of
is it
some.
minus 1 or
Okay, but I want an integer, right? So
like if we consider xn of 3, sir, so
Mhm.
that is the highest. So log of that 3 plus 1 would be
So,
like log.
so is this correct? Log 2 to base 1. Floor of log I to base 2.
Yes.
So
Yes,
if I put I equal to 0, sorry, if I put I equal to 1, then log 1 is 0, so k is 0. If I put 2 or 3, then log I to base 2 is going to be a 1 point something, 1.0 or 1 point something else. And that is, and floor of that is going to be 1. 4 to 7, it is log I is going to be between 2 and 3. So floor of that number is going to give me 2. And then 8 up to 15, it is going to be a number, log of that number is going to be between 3 and 4. So the floor is going to be 3 and so on. Okay. Is this clear?
Yes, sir.
Yes, sir.
Okay, good. So now we have a formula for k of xn, right? And so we know that k of xn of I is exactly equal to the floor of log I to base 2. Okay, that is very good. But now we want something, we want a general bound to work for every p of xn. So we know that the expected length is summation I going from 1 to a plus 1 to the n of k of xn of I times the probability of that sequence. Right, so we know exactly what this is equal to, but unfortunately we don't have a good bound for this yet. Okay, so now let's try to think. Can for any general, so I want a bound which works for any pxn, right? It doesn't matter. The only thing I know is that pxn of xn of 1 is greater than or equal to pxn of xn of 2 and so on. Right? So the question is now what do we do? How do we get a bound on this particular quantity? We know this, but then this can be anything, right? So for this, I'm going to do a trick, and it is of course not obvious if you, beforehand, but in hindsight you'll see that yes, that is true. So the claim is that pxn of xn of I. So let me just make sure that I'm doing this correctly. All right. So this is going to be less than or equal to 1 over I. This is the claim. So if I look at the ith largest sequence, then it is always going to be less than or equal to 1 over I. Okay.
Sir,
Yes.
in summation,
Yeah.
that
This one?
limit is that is just a plus 1, sir. Some power in you put no.
No, so the size of the alphabet is a plus 1, right? But then the total number of source sequences is a plus 1 to the n, right? We're looking at all possible n length sequences,
Okay.
right? So if you go back here, the assumption is that each xi can go from 0 up to a. So the total number of sequences of length n is a plus 1 whole raised to the n.
Yeah. Okay, sir. Thank you.
Okay. So now my claim is that now pxn of xn of I is less than or equal to 1 over I. Now let's see if that this is true for small I. So obviously pxn just I don't want to write xn of 1, xn of 2 and so on. I just say pxn of 1 Now this is obviously less than or equal to 1 because probability always has to be less than or equal to 1. Now I'm also saying that Pxn of 2, the second highest, the sequence with the second highest probability should have probability less than or equal to a half. Okay. Now why might this be true? What happens if it is greater than half? Can that happen?
No, sir.
Why?
Because then it would be the highest probable sequence.
Correct. So if this probability were greater than half, you know that Pxn of 1 is greater than Pxn of 2. So if this is greater than half, then Pxn of 1 should also be greater than half, and the sum would be greater than 1, right? And similarly, so if Pxn of 3 has to be less than or equal to 1/3.
So can you repeat the last statement, sir, that you just said, sir?
Okay. I'm going to make it more formal, but let's assume that Pxn of 2 is greater than half. Okay, so assume we'll get a contradiction. Assume that Pxn of 2 is greater than half, right? But then what about Pxn of 1? Right? We know that this is greater than or equal to Pxn of 2. Xn of 2, correct? So this should be greater than half, right? But then what is Pxn of 1 plus Pxn of 2? This would be greater than half, strictly greater than half plus half, which is equal to 1, right? But then the sum of the probabilities can never be greater than 1, right? So that's a contradiction. So it can never happen. Correct. So either that is wrong, or Pxn of 2 is not the second largest sequence. It is the largest. It has the highest probability. Which so whatever it is, you arrive at a contradiction. All right. So in general, suppose if Pxn of I is strictly larger than 1 over I for some I, doesn't matter which I it is. If it is greater than 1 over I, then obviously summation j equal to 1 to I Pxn of j. Now all of these so all of these values should be greater than 1 over I, right? Because all of them are greater than or equal to Pxn of I, which is greater than or equal to I times Pxn of I, because we're summing from the largest probability to the ith largest probability. So all of them should be greater than or equal to the ith largest probability, and there are I terms in this summation. So it is I times Pxn of I, which is strictly larger than I into 1 over I, which is 1. Right? So this is not possible. And therefore it is a contradiction. Right? So it's a proof via contradiction. So this is not possible. So it must mean that Pxn of I is less than or equal to 1 over I for all possible I.
Sir,
Yes.
can you repeat that? So, like from summation j equal to 1 to
Okay.
how you are
Okay.
taking.
So I have summation. So okay. So let us assume that Pxn of I is strictly larger than 1 over I for some I. It doesn't matter which I, but it is strictly larger than 1 over I. Okay. So now what can you say about pxn of 1, pxn of 2, pxn of 3, all the way up to pxn of I minus 1? They must all be greater than or equal to pxn of I, right? Let me maybe put this here to get more space. Okay, so what does this mean? Well, we know that pxn of 1 is greater than or equal to pxn of 2, and so on, pxn of I, right? So all of these terms are greater than or equal to pxn of I, and the claim is that this is strictly larger than 1 over I. So all of these terms are strictly larger than 1 over I. All right, so now let us start with this expression over here. So it is summation j going from 1 through I. So I'll sum the probabilities of the first I largest probability terms. Right, so this is pxn of 1 plus pxn of 2, so on up to pxn of I. Right, and I know that all of these are greater than 1 over I. So it is strictly larger than 1 over I plus 1 over I plus 1 over I, so on, plus 1 over I. Correct? But how many terms are there over here? There are I possible terms, right? 1, 2 up to I. So it is I times 1 over I, which is 1.
Okay, sir. Understood. Thanks.
Okay. Any questions? Okay, so we know that the ith largest probability is always going to be less than or equal to 1 over I, which is a neat observation. Right? So now we have a good bound, right? So we have this. Now let us see. Okay, so we know that p xn of I is less than or equal to 1 over I. Now I'll write this in a different way. So this implies that I is always going to be less than or equal to 1 over pxn of I. Okay, or 1 over pxn of xn of I. Okay, this is a very good thing to know. So I is always going to be less than or equal to this. Now let us plug that in here in this particular expression. So now, okay, so we know what, so this is equal to summation I equal to 1 to a plus 1 to the n times pxn of xn of I times kxn of I, but we know that this is equal to the floor of log I to base 2. Okay, so this is an exact expression. Now this, as we know, as we've just seen, we know that I is less than or equal to 1 over pxn of I. So if I equal to 1 to a plus 1 to the n, pxn of xn of I times the floor of log 1 over pxn of xn of I. Right? So this, now if I sort of just ignore the floor, in the worst case, it is obviously going to be less than or equal to summation I equal to 1 to a plus 1 to the n. Okay, so this is going to be less than or equal to. So the floor of the log is obviously going to be less than or equal to the log. So Pxn of xn of I log 1 over Pxn of xn of I, right? Which, I mean, if you can also rewrite this as the summation over all possible xn of P of xn log 1 over P of xn, which is just the entropy of the sequence. So this is a quantity that we define as the entropy of Pxn. All right. So I've done nothing over here. We first designed a compression algorithm for which the length of the ith largest sequence, the compressed length of the ith of the sequence with the ith largest probability is log I to base 2, floor of log I to base 2. And then we saw that the ith highest probability is always going to be less than or equal to whatever 1 over I, or I is always going to be less than or equal to 1 over the ith largest probability. And I just substituted that in the expression for the expected length, and since log since floor of log is going to be less than or equal to the log, this is less than or equal to Pxn log 1 over Pxn and sum over all possible xn. Okay, and this quantity over here, where we are going to give it a special name, it is the entropy, which we saw in the very first class, right? So it is the entropy, and this is going to be a measure of how much information the sequence contains. Okay, so this sort of connects the entropy to the information content of the source, or the entropy to the data, the compressed length. So this says that the compressed length has to be, so there is a scheme for which the compressed length is less than or equal to the entropy. Okay, but this is a pretty tight bound, right? So we know that for this is less than or equal to the entropy, but this is off by at most 1 bit, right? So I said this is the floor of the log is less than or equal to the log, but it is also greater than or equal to log of this minus 1. So if you just plug that in this expression over here, you'll get that this is always going to be greater than h of xn minus 1. Okay, so asymptotically, if you look at expectation of k of xn by n, that is going to be h of xn by n. Okay, so if you look at this particular quantity, the limit as n tends to infinity the expected value of k of xn divided by n. So this is the asymptotic average rate. This is going to be the limit as n tends to infinity h of xn divided by n. Okay. So this quantity has a special name, the limit as n tends to infinity h of xn by n. It is called, so h of xn is the entropy. So the normalized entropy as n tends to infinity, this is called the entropy rate. Right? So if this limit exists, then it's called the entropy rate. And note that we made absolutely no assumptions on the source sequence. It could be IID, it could be a Markov chain, it could be stationary, it could be ergodic. It doesn't matter. But you can always construct, well, in principle, theoretically, you can construct a compressor for which the expected length is close to the entropy of the source sequence. It is no larger than the entropy of Xn. Right? So can construct compressor for which the average rate is equal to the entropy rate. All right. And this, in some sense, is a fundamental result in information theory, that the optimal rate of compression is equal to this particular quantity. We constructed an optimal compressor, right? We can't really do any better than this. And practical compressors have far more constraints than what we put in. But even then, they do get close to the entropy rate. So therefore, the optimal rate of compression is equal to the entropy rate. For an IID sequence, we'll see that the entropy rate turns out to be equal to, for IID Xn, the entropy rate, as we'll see shortly, is equal to the limit as x tends to infinity h of xn by n. So this depends only on the marginal and is equal to h of x, which is, so it's not an n letter term, it is just this px of x log 1 over px of x. Okay, so this is the fundamental connection between entropy, which is this term over here, with the problem of data compression. All right, any questions? Okay, so this was basically variable length compression, right? And we assumed, again, always keep that in mind. So we're doing variable length compression over here, and we have no other constraints on computational power. We know the entire distribution at both the encoder and the decoder. This is available for free because you need it to compute this table, right? You need to order all the sequences in the decreasing order of probability. And finally, what that guarantees is that what this construction guarantees is that the expected length is close to the entropy. And that turns out to be the fundamental limit. You can't do any better than that. Okay, so you can prove a similar result even for fixed length compression, for which the probability of error should be vanishing with n. All right, even for that, we'll see that the following holds. So basically, what Shannon proved in his original paper, this was so the proof that I gave is kind of more modern, and it's for variable length compression. But then what Shannon originally proved in his paper was that if you have an IID sequence, or in fact any stationary and ergodic sequence, then it is possible to construct a compressor for which the rate is arbitrarily close to the entropy or the entropy rate. and the probability of error of the fixed length compressor, fixed length compressor, for which the rate is arbitrarily close to the entropy and the probability of error vanishes with n. As n tends to infinity, the probability of error becomes smaller and smaller. Okay. So what he proved had two parts. So one is achievability, that it is possible to construct. He doesn't give an efficient scheme. He doesn't give a good compressor. The computational complexity of designing the compressor and the decompressor could be exponential time. In fact, it is exponential time. But then, nevertheless, in principle, it is possible to construct. If you had absolutely no computational restrictions, it is possible to construct encoders and decoders for which the rate is close to the entropy. So that is the best that you can do. But in fact, the second part of the result that he proved was that if you try to compress at a rate below entropy, so you try to design, no matter how you try to design the compressor and the decompressor, no matter how much computational power you invest in, if the rate is strictly less than the entropy, then the probability of error, you can never make it go down to zero. In fact, the probability of error tends to 1 as n tends to infinity. And this is for fixed length compression. And right now what we proved was a similar result for variable length compression, that it is possible to construct compressors and decompressors for which the rate is equal to, the asymptotic rate is equal to the entropy, and the compressor that we designed was optimal. You can't do any better than that. So no matter how you try to construct your compressor and decompressor, the average rate is always going to be no smaller than the entropy, right? The entropy or the entropy rate for general sequences. All right. Any questions? Okay, so before we end the class, let's just do a very quick calculation. Let us assume that the sequence is IID. So Xn is IID Px. So what is h of Xn by n? Right, so it is a sum over all possible Xn, P of Xn log 1 over P of Xn, right? So now we know that this is an IID sequence. So I can write each P of Xn as the product I going from 1 through n, Px of xi log 1 over product I going from 1 through n of Px of xi, because it's an IID sequence. So by definition of an IID sequence, the joint probability is just equal to the product of the marginals. So this is summation I going from, so summation over all possible xn, product I equal to 1 through n, Px of xi. But then I can split this, right? So the log of the product of terms is just the sum of the log of the individual terms. So summation I going from 1 through n of, let me say, j going from 1 through n of log 1 over Px of xj, right? Now I can just interchange these two summations. I bring this in and take the summation outside. I get summation j equal to 1 to n of sum overall xn Px of x product I equal to 1 to n Px of xi log 1 over Px of xj. And now I can just marginalize with respect to all other xi's not equal to xj. And that just gives me summation j equal to 1 to n summation overall possible xj Px of xj log 1 over Px of xj. But all of these are the same for all j's, right? So this is just n times summation overall possible x Px of x log 1 over Px of x. Okay, so my bad. So this is just h of xn. Right, so if the sequence is IID, then h of xn is n times h of x, or the entropy rate, the limit as n tends to infinity h of xn by n, this is equal to h of x. All right. Okay, so let's stop at this point. So you should try to work this out on your own. Take pen and paper. It's a simple derivation. It just uses the property that the joint probability is the product of the marginals. So try to compute this entropy h of xn for IID sequences for first order Markov chains and so on. It's a simple calculation, and you'll see that for such distributions you have very simple expressions in terms of the marginals, or in terms of the marginal and the conditional probabilities. Okay. Any questions?
Sir, can you give some hint about question number 5 of the homework, sir?
I don't remember what question number 5 is. So can you just remind me what that was?
It was like bounds on the binomial coefficients. There were 4 or 5 bits to it, sir.
Okay. So
Like, can you just give us like what could be the starting point or what reference? Like there were some proofs were there, sir. So like where should we start with this thing, sir?
correct. So typically you start. So if you have you'll have to prove it step by step. So if you can, so the first part should be okay. Just try to rearrange the terms in that inequality, and you should be able to prove that. And for the second part, you just write the full expression for the binomial coefficient in terms of n minus 1, n minus 2, and so on, and then you try to use that and part 1 to prove part 2. Does that help?
Yes, sir. Yes.
Yeah. So the first part, it's not very difficult. You just have to rearrange the terms in that particular inequality and think about it a little, and you'll see why that is true. So another hint is that remember that n is always going to be greater than k. So n is greater than k, which is greater than L. So if you sort of rearrange the terms over there, and try to think about it, you'll see that one side has to be greater than or equal to the other side. So it's just rearrangement that should give you what you want. The second part, of course, you use the first part to prove the second part. For the third part, you just use Stirling's approximation and then simplify. There's nothing more to it. It's just algebra and sort of simplifying it in a particular fashion. So you don't need any extra results. You just have to rewrite things, simplify things in a very particular way.
Right, sir. Thank you.
Okay. Any other questions? Okay, so if not, we meet next week. So see you all then.